All right, calculating pH changes in buffer solutions. Okay, let's look at our plan of attack here. Okay, so this is how you're going to calculate buffer solutions after adding acid or the base. So you had a weak acid solution and you added its conjugate base, or you added sodium hydroxide to get that conjugate base. Um, Really, there are two tables that will be in use, and most of the time an ice table will not be necessary since we can do Henderson-Hasselbalch, but there's two tables. And no one knows what to call the first table. Your book calls it's an ice table, but it's not an ice table, so some call it an ice-like table. Your book calls it a stoichiometry calculation, whereas an ice table is an equilibrium calculation. You're going to see I'm going to sometimes call it an ICF table instead of an ice table. It's ice table-like. It's going to look kind of like an ice table, but it's really just going to be an ice-like table where we just calculate stoichiometry, where we're going to do the same stuff we did in Gen Chem 1 with stoichiometry, but in table form. And the deal with these ice-like tables, all the values need to be in moles. You have to have moles. Note for ice tables, the equilibriums calculation, you need molarity. You have to have the molarity. All right, ice-like tables or ICF tables or stoichiometry calculation tables calculates what happens when you add the acid or base and it reacts with what is in there, and you can calculate what's left. Ice tables are standard equilibrium calculations. Easiest way to look at this is let's work a problem here. All right. You have a buffer solution that is 0.1, or excuse me, it's 1 liter that is 0.1 molar in CH3COOH and 0.1 molar in NaCH3COO. Note that there are multiple ways to write acetic acid. HC2H3O2 is the same as CH3COOH. When you get to organic chemistry, we tend to write it more this way. All right, so note, we have 1 liter solution. That's a nice volume. 0.1 molar acetic acid, 0.1 molar sodium acetate. The acid and its conjugate base. Concentrations more than you get from just dissociation, so we have a buffer solution. You are then going to add 0.25 moles of a strong acid to this solution. And we are going to assume for this problem to make it easier that there's no volume change here. In the later problems, we're going to worry about volume change just so we can make sure we can do the normal calculations. We're going to assume no volume change. We're going to assume the volume stays at 1 liter, even though you added this little bit of acid to it. So, two questions. What is the pH of the original buffer solution? And what is the pH of the solution after you add the acid to it? So this solution here that's 0.1 molar acetic acid, 0.1 molar sodium acetate, what's its pH? After you add the acid, what is the pH? We would predict, since this is a buffer solution, that the pH doesn't change too much. Well, let's dig in. Well, good news. We have a buffer solution to begin with, right? Since we have a buffer solution to begin with, we can just use Henderson-Hasselbalch. We know that Ka is 1.8 times 10 to the minus fifth for acetic acid, so pH equals pKa plus a log of the acetate concentration divided by the acetic acid. pH equals 4.74 plus the log of 0.1 divided by 0.1. This is something interesting. When you take the 0.1 divided by 0.1, you get 1. The log of 1 is 0. So 4.74 plus 0 is 4.74. This is just a handy thing to put in your old noggin here. Whenever the concentration of HA and the concentration of A minus in a buffer solution are the same, pH equals pKa. When you have just as much A minus as you have HA, pH equals pKa, 4.74. Very nice. All right. So now we're going to add the acid. We're going to, question 2, we're going to try to calculate the pH solution after adding the acid. So the question we have to ask ourselves, okay, what reaction is going to occur when we add the acid? Once this acid is added, what's the acid going to react with? Well, in the solution is acetic acid and acetate, its conjugate base. our added strong acid will react with the conjugate base acetate because acids neutralize bases. So when we add this 0.25 moles of acid here, we know since we added this extra strong acid, it will react with the conjugate base acetate. So we then need to do the ice-like table, or what I call an ICF table, where we have our added acid reacting with the conjugate base to form acetic acid. And acid plus the conjugate base forms the acetic acid. Note, this was a strong acid, and acetate ion is a weak base. Strong acids and weak bases, when they react, they go 100%. This is not equilibrium. A strong acid always reacts 100% with a weak base. This is a 100% reaction. So there's no equilibrium here. This reaction goes 100%. That's why we cannot call this an ice table. So I like to call it initial, change, final, ICF. So it looks kind of like an ice table, but we aren't calculating equilibrium, we're calculating a final, and we can actually get the numbers because this is really just a stoichiometry calculation. Recall we had 0.1 moles. Well, we had, here's something. Note ICF tables, these ice-like tables must be in moles. So we have to convert to moles. Well, okay, how do we do that? Luckily, this problem, whoever thought this up, is being easy on us because we have 0.1 molar acetate, but we have 1 liter of solution. Which means if we have 1 liter of solution and our concentration is 0.1 moles per liter, we have 0.1 moles of acetate. So this is 0.1 moles of acetate. Note our problem said we added 0.025 moles of our strong acid. So our initial strong acid is 0.025 moles. Our problem said we also had 0.1 molar acetic acid up here, so we got 0.1 moles of acetic acid. What's our change? Well, this goes 100%, so now we just have to look at which of these reactants is the limiting reagent. Well, we've got the moles. Note it's 1 to 1, our stoichiometry. So if we have 0.025 moles of H plus and 0.1 moles of acetate, we can see that this is a limiting reagent. All of it will be gone. We'll use up minus 0.025 moles of H plus. We'll use up minus 0.025 moles of acetate, and we will add 0.025 moles of acetic acid to this solution by running this reaction. So our change will be 0.075. Our final change will be these. Our final will be 0 H plus. It all got used up by the acetate since it's a limiting reagent. We had excess acetate, 0.075 moles excess of acetate. And we have now 0.125 moles of acetic acid for this reaction. Okay, note as an aside, since it's all in 1 liter, because we said there was no volume change at this point, that makes our concentration of acetate 0.075 molar, our concentration of acetic acid 0.125 molar, no extra H plus left over. But we're not done because we need to know the pH of the solution after adding acid. Now we've just got the concentrations of these two beasts. But let's examine this. What now do we have in solution? We don't have any H plus, but we do have a decent amount of acetate and we have a decent amount of acetic acid. We still have a buffer solution here. All right. And so if you have a buffer solution, how do you solve for a buffer solution? There are 2 ways, the long way and the short way. Let's start with the long way. I recommend not doing this on the exam because it takes too long. But here's the long way to do it. Do an ice table. Since we have 0.075 molar of acetate and 0.125 molar acetic acid, just do an ice table. No, so we've got the Ka for the reaction, so we need to write the Ka reaction since we were given Ka for acetic acid, 1.8 times 10 to the minus 5. So the Ka equation is acetic acid in equilibrium with H plus CH3COO minus. Our initial amounts were the 0.125 molar, none of this before dissociation, 0.075, minus x plus x plus x, 0.125 minus x, 0.075 plus x. Plug everything in. We can note, because our equilibrium constant, our acid dissociation constant, is so small, we can ignore the minus x and the plus x here. Math becomes easy. pH is 4.52. Note, walking through it by saying it when it's already written down is easy. It's going to take you a little bit longer to think through this and write it out. But you might be saying, okay, but wait a minute, didn't you say if we have a buffer solution, we can use Henderson-Hasselbalch? Yeah, that's the short way. After our ice-like table, note we have 0.125 moles of CH3COH, 0.075 moles of acetate. The nice thing about Henderson-Hasselbalch equation, pH equals pK of log of concentration of A minus divided by HA. But at this point, you can actually just put in the moles. You don't actually have to convert to molarity here, because if you had 0.075 moles of acetate divided by 1 liter, gives you molarity, over 0.125 moles divided by 1 liter, those 1 liters are going to cancel out when you take H or A minus divided by HA. So even if we weren't in 1 liter solution, even if we're in half a liter of solution, if we're in 250 milliliters of solution, with Henderson-Hasselbalch, since they're mixed together, volumes will always cancel out. You can just stick the moles in here. You do not actually have to go from the number of moles at the end of your ice-like table into molarity. You can just stick the moles in here, and our pH is 4.52, the same thing we got here. And note, we added some acid. We added 0.025 moles of acid, and the pH is now 4.52, but our original pH of our solution on the previous page was 4.74. So adding some acid dropped it from 4.74 to 4.52, only about 0.2 pH units for when we added some strong acid to it. All right. Okay. Let's look at some more buffer stuff to finish out this section in this video here. More buffer stuff. Okay. Here's the thing with buffers. They do their best when the concentration of HA is fairly close to concentration of A minus. If you've got a good buffer, if you've got like 0.1 molar HA and 0.1 molar A minus, or 1 molar HA, 0.8 molar A minus, when those two numbers are about the same, it's right in the middle of your buffer region, and therefore that's a good buffer. When these two are about the same, that means your buffer solution can handle just about as much acid that you add to react with A minus, or can handle just about as much base as a decent amount of base to react with HA. Buffer solutions are most effective at high concentrations of HA and A minus. The higher you have of HA and A minus, the more acid or base you can add. A 0.1 molar HA, 0.1 molar A minus buffer solution will not be able to handle as much acid or base added to it as a 1 molar HA and a 1 molar A minus. So if you're making buffer solutions, you tend to find they're around 1 molar or 0.1 molar, decently strong. If you had a 0.0001 molar buffer solution, 0.0001 HA, 0.0001 A minus, that can't handle that much acid. The range of a buffer in general is from the pKa minus 1 to the pKa plus 1. Meaning if you have an acetic acid buffer, the pKa for acetic acid is 4.74, which means if you make these buffer solutions, it will tend to keep the pH from about 3.74 to about 5.74 or so. And note, if you're only adding little bits of acid or base, it stays pretty close to 4.7. But this tends to be the buffer range. If you add, which means you can add, in general, the concentration of A minus is 1/10 the amount of HA, or the concentration of A minus is 10 times the amount of HA, because note, pKa is a log scale, base 10 scale. So each pKa unit is 10 times more Ka value. All right. And the last thing is buffer capacity, the amount of acid or base that can be added to the buffer solution without large pH changes. And that's what we're talking about. When you've got these two at about the same amount, roughly the same concentration, and it's a high concentration, like 1 molar, then that has a large buffer capacity. It's going to take a lot of acid added to this buffer solution of 1 molar HA and A minus before it's going to change appreciably from the pKa value of 4.74 for acetic acid. If you have very low concentrations of these, you have very low buffer capacity. It's not going to be able to handle much. And that's the thing I've seen a mistake made a number of times in the lab when I say, okay, go make this buffer solution, and a student will make a buffer solution, and then they're running the reaction, and it doesn't work. Why didn't it work? Well, what concentration did you make the buffer solution? 0.01 molar. Oh, well, see, you've got very low buffer capacity. It couldn't handle the amount of acid that was going into it. So you need to make strong buffers, 0.1 molar or better 1 molar buffer solutions that can handle just about anything you throw at them. All right, so the next video then, let's get some practice. In the next video, we're going to work this little buffer problem here. It's a 6-part buffer problem. Something you might see on an exam, although frankly it's a little long for an exam. You'll find out when you look at the next video and we work through this buffer problem.